All right. I promised you we would learn about radians. There are two ways to measure angles. One of them is degrees. One of them is radians. Degrees are really nice in the real world. If you're going to build a building, design a car, you're going to work with degrees. All right? But degrees mathematically lack a quality that we really need. And one example of that is if you want to graph a trig function like sine or cosine. So if you have a graph, the x-axis is angles, that's our domain, our inputs, and then the y-axis is just a series of percentages. For instance, the sine of 30 is 0.5, meaning the wall is 50% as long as the ladder. Or if the ladder is length 1, then the wall is 0.5. So if the ladder is length 1, we can actually change this from a percentage to a length. And that's huge. We talked about that quite a bit. But in order to graph the sine function proportionally, we need the labels on the y-axis to match the labels on the x-axis. Okay? I don't know if that makes any sense to you. Yeah, so that the 1 and the 1 are equal. The only trouble is these lengths are in terms of the ladder, and the angles, there's no such thing as a length for an angle. Well, at least not yet. So the ladder can be as high as one ladder, and then you would have 0.5, 0.25, 1/8, and so on. So the y-axis only goes up to 1, because that's as high as the wall can be, as 100%. Well, there's no relationship between the length of the ladder and the angles. And that's a problem, because if we graph the sine function, and it's supposed to look like that, if we stretch the angles out too far, then it's going to be wider than it needs to be. If we smash the angles too much, then it's going to be steeper than it needs to be, and the shape of the sine function is really important. So degrees won't do it for us. We can't graph the sine function in degrees and guarantee that it's proportional like it should be. Now, that's slightly untrue because we know how to graph them in radians, and once we graph it in radians, we can compare it in degrees. So you actually can graph it in degrees, but without radians, you're not sure that the graph actually looks like it's supposed to. So I've created this worksheet to show you what a radian is. The bad news, radians make very little sense in the real world. Nobody runs around with a radian protractor. I've never even seen one. They don't exist. So radians are used theoretically, and degrees are used practically. But radians do a couple things that are really nice that degrees don't do. So remind me again what a degree is. What does a degree do? It's a 1/360th of a circle, but what does it actually do? It rotates. So on this little dial I've constructed, that's a rotation. Does the length of the dial change the rotation? If I were to make this dial 4 times longer, would that still be 25 degrees? Yes. Okay? Radians are different. Radians are not rotations. They're distances. Okay? So you take your dial, I'm going to draw the dial here, and no matter how long the dial is, you call it 1 unit. More specifically, 1 ladder. The length of the dial is 1 ladder, just like in a right triangle we want the length of the hypotenuse to be 1 ladder. Okay, so no matter how long the dial is, you call it 1. And then instead of measuring the rotation of the dial, you measure the distance traveled by the tip of the dial. So imagine you put a marker right here, taped it onto the dial, and as you turn the dial, the marker is going to trace out a circle. Right? Is that a good circle? Yeah. I took college geometry twice. No. So, Wow, cool. So instead of measuring the rotation, we're going to measure the distance. So radians, I mean, you can rotate with radians, but that's not where they come from. Radians are the distance traveled by the dial in terms of the length of the dial. Now, obviously, if my dial is smaller, the distance is going to be smaller. But when you compare the distance traveled to the length of the dial itself, then it's always the same. It's always the same rotation. So here's how we define radians. We take our dial, 1 unit, okay? And then as we rotate, we measure the distance. So that's like a fourth of a radian, of a radius, or a ladder. I'll just put it in terms of ladders. So my radius is 1 ladder. That's a fourth of a ladder, a half of a ladder, 3/4 of a ladder, and a full ladder. As soon as the distance traveled is equal to the radius, you stop. And that angle right here is called 1 radian. That's where radian comes from. Now, in the little red circle, is it going to be different? So here's my radius. That's a really terrible circle. A quarter, a half, 3/4, and a full radius. What do you notice? The angles are the same, okay? But the distance traveled is different. So radians are tied to the radius of the circle. And no matter how big the circle is, we call the radius 1 radius, or 1 ladder. Okay? So you see this picture down below. So in both cases, the radius is 1 unit, and the arc length, which is a portion of a circle, that arc length is the same distance as the radius itself. When that happens, as soon as you get to the 1 unit mark, then we call that angle 1 radian. Are we out with those? Yeah, we got these Thursday. Okay, so how do I figure out how big that is? How many degrees are there in 1 radian? How are we going to figure that out? Right, 2 pi r. So if I were to finish the circle, then the distance traveled by the dial is 2 pi r, the circumference. Well, what is r? 1. So it's really just 2 pi. So 2 times pi, that's the circumference formula of a circle. So there are 6.28 radians in a circle, and that's how we write it. Well, that number is irrational. It's nasty, terrible, awful number. Okay? And just so you know, if you were to take a string and cut it as long as the radius, and you were to wrap it around, it would go around 6 times and 28% more. No matter how many times you put that string out, it would never end on that standard position ever again. So if I were to say, okay, there's 1 radian, there's 2 radians, 3, 4, 5, 6, and then you go around again, 7, 8, 9, 10, and so on. You're never, ever going to land there again. In fact, you will never land in the same place twice. That's how irrational numbers work. You're never going to hit the same place twice. So radians are kind of impractical for that. Okay, they don't divide the circle evenly. Okay, so we don't like this value at all. It's annoying. So instead of using 6.28 radians, we rely on the information from the formula. And we say, in a full circle, there are 2 pi radians. So we're going to label the standard position as 0 or 2 pi. whenever we talk about radians, we always use pi. Now on the ACT, maybe they'll throw in a non-pi radian. You'll see it in some textbooks, but really nobody does it. So 6.28 radians is the same thing as 2 pi radians. But if you leave it in pi form, you don't need the RAD. The pi itself counts as the units. Okay? So you can write the RAD if you want, but as long as there's a pi in your answer, then you don't need to write the RAD. Okay, so how far is halfway around the circle if the full circle is 2 pi? 1 pi, or just pi. Okay? What would the 90-degree mark be? 1/2 pi. So you could do 1/2 pi, you could do 0.5 pi, you could do 1 pi over 2. But the one that we usually use is just pi over 2. Okay? What about 3/4 of the way around the circle? It's not pi fourths. Well, what's halfway between pi and 2 pi? 1/2 pi. In fraction form, that's 3/2 pi. So you can either write 3 pi over 2 or 3/2 pi. Those mean the same thing. And you'll see it written both ways. No, it doesn't matter. Yeah, those are so interchangeable. Everybody knows both of them. Okay, so how do we convert? Well, how many radians, how many degrees are there in 1 radian? Well, we know there are 360 degrees in a circle. We also know that there are 2 pi radians in a circle. So let's divide the two. So 360 divided by, you need to put this in parentheses, 2 pi. 1 radian is 57.29 degrees. Okay? Well, guess what? If your degree measure is a whole number, your radian measure will be irrational. If your radian measure is a whole number, your degree measure will be irrational. So they don't really mix very well. Unless you leave the pi on, then it becomes easier. So if I had 65 inches, how do I convert that into feet? Times it, divide it by 12. Why does that work? Well, if I have a number and I multiply by another number, doesn't that change its value? So if I have A and I times it by something, I'm going to get something other than A, right? Not unless that number is 1. So any number times 1 is itself. Well, can I divide by 12 without changing its value? Explain. Well, I'm allowed to multiply by 1, right? Well, I know that in 1 foot there are 12 inches. So what is 1 foot divided by 12 inches? 1, right? Because 1 foot equals 12 inches. Everybody agrees? So I divide by 12 inches, and I get this equals what happens on the other side. That becomes a 1. So I'm allowed to multiply by 1 without changing its value. Now, if there are units attached, I'll change how it looks, but its length will not change, as long as the top and the bottom are equivalent statements. Well, notice, what is inches divided by inches? 1, so that cancels that. So 65 times 1 foot divided by 12, 65 twelfths is 5.5 0.041 feet. That's the leftover. That's why conversion works, because you're allowed to multiply by 1. Well, if I change gears and I say 6 feet, what would I times that by to get inches? There are 12 inches over 1 foot. How did I know that was the way to do it? I need to cancel the feet and end in inches. So feet cancel feet. 6 times 12 is 72 divided by 1. Those are equivalent statements. And I didn't change the length, I just changed how it appeared in unit form. But by multiplying by 1, I didn't change the value, the actual value. So if I had 60 degrees, I need to multiply it by something that will get rid of degrees and turn it into radians. Any equivalent statement would work. Okay, we could do 2 pi equals 360. We could do 90 degrees equals pi over 2. Yes, this is the easiest one, because that is in simplest form. Okay? So, I'm going to times this by what? What do I want to keep and what do I want to get rid of? Get rid of degrees and keep radians. So on top, I'll put pi, and on bottom, 180. So, right off the bat, I notice that degrees cancels degrees, and I get 60 pi divided by 180. Oh, shoot. 60 pi divided by 180. Ugh. That number's awful. Yeah, well, so my answer is 1.04 radians. But nobody does it that way. We don't like irrational numbers. So what we're going to do, leave the pi out of the formula and stick it in at the end. So 60 over 180, that's a lot nicer decimal, and I can turn it into a fraction, and I get, push math, fraction, enter. So 1/3 pi, more commonly known as pi thirds. Do you see how I did that? So let's look at the first one, 50 degrees. So for 50 degrees, I'm going to times it by pi over 180. When you calculate it, never plug the pi into your calculator. Okay? If you're looking for an angle, if your answer is going to be an angle, never plug pi into your calculator. Just use the coefficients on pi, 50 over 180, and we get 5 pi over 18. Can you guys handle that? So this is going to be part of your homework. Yeah, so you plug this part into your calculator and then put the pi on the end of the answer. Okay? And your pi can either go here or it can go to the side. It doesn't matter. If you put it in the denominator, that's wrong. So on top or to the side, that's the same thing. Okay? Well, let's go over to the radian side of things. If I'm looking at the angle pi over 4, what conversion factor am I going to use? Well, I want to get rid of pi, and I want to keep degrees. So degrees goes on top, and pi goes on bottom. And again, you could use any equivalent statement. The pi's cancel. So what's left here? A 1. So 1 times 180 divided by 4 times 1 is just 180 over 4, which is 45 degrees. Okay, go down to the third one, 3 pi over 2. Remember, I want to get rid of pi. So pi goes on bottom, 180 goes on top. Pi cancels pi, and I'm left with, is it 3 times 180 over 2, or is it 3 halves times 180? Well, let's try it. 3 times 180 divided by 2, that's going to give us 270. What about 3 halves times 180? Doesn't matter. Because multiplication and division commute. So you really can't screw it up. As long as you have everything on top and everything on bottom, you can't mess it up. What about 3 pi? Times it by 180 over pi. Pi's cancel, and it's just 3 times 180. You can divide it by 1 if you want, but there's no need. You can write 3 pi over 1, but that's not going to change your answer. Yeah, the second column you're going to turn from radians to degrees. Okay, turn the page. Coterminal angles. So let's start with an example that we know. 40 degrees. How do I create a positive coterminal angle to 40 degrees? Add 360. So that would be 400 degrees. Now 40 and 400 are exactly the same angle. We don't care how many times you go around the circle. We don't care what direction you go. Wherever you stop, that's the important thing. And 40 and 400 stop in the same place, so they're the same angle. Okay? Well, what if I wanted a negative coterminal angle? So we would do 40 minus 360, which is negative 320. So now we have 3 angles that all land in the same place. Which quadrant is that, by the way? Quadrant 1. Good. Okay. So let's do the same thing in radians. So I'm just going to quickly convert this. Pi over 180. 0 cancels 0. 2 pi over 9. So 40 degrees is 2 pi over 9. Okay? How am I going to find a positive coterminal angle that lands in the same place as 2 pi over 9? I'm going to add 360 degrees, but in radians, a full circle is 2 pi. So I'm going to add 2 pi. Okay? I'll show you the calculator way first, which in my opinion is slower. So 2 pi divided by 9 plus 2 pi. Oh, wait a minute. I don't like that. If I tried to create a fraction out of that, why didn't it give me a fraction? It's irrational. So remember, leave the pi's out. So 2/9 plus 2, turn that into a fraction, and I get 20/9. And then once I have the fraction, then I put pi next to it. Can you guys remember that? Now, just to show you, 400 divided by 180 is 20/9. So you could always take an angle, convert it to degrees, add 360, and then convert back to radians. That's kind of a pain, right? Okay, so let's minus 2 pi. So I want you guys to do this one. What is a negative coterminal angle for 2 pi over 9? We'll do it in your calculator. Two ninths minus 2 is negative 16 pi over 9. And if I did negative 320 divided by 180, I'm going to get the same value. Okay, now, I don't ever do it that way. That's way too slow. Okay? You can do these in your head very, very easily. All right. So this is 2 pi, and this is 1 pi. So we're going to consider the angle 40 degrees, which is in quadrant 1, 2 pi over 9. So this is 2 pi over 9. Now, if I were to divide the entire circle into ninths, are you guys confused? Have I lost you? No? Oh, okay. So, how many ninths are there in that angle? How many ninths of pi are there? Well, how many ninths are there in 1? Okay, this is really important. Some of you aren't paying attention. So this is 9 over 9. How many eighths are there? So this is also 8 over 8, or 7 over 7, or 6 over 6, right? Because it's 1. All right, if we go to the other side, how many ninths are there in the full circle? So this is 18 ninths, or how many eighths? 16 eighths, how many sevenths? 14, how many sixths? Does everybody understand that? Half of the circle is 9 over 9, or 8 over 8, or 7 over 7, right? A full circle is always double the denominator. So if I have 2 over 9 and I add a full circle to it, how much am I going to add? Well, 18 ninths. So what is 2 over 9 plus 18 over 9? 20 over 9. Okay. What is 2 over 9 minus 18 over 9? Negative 16 over 9. So they're really easy to do. If I had the angle 3 pi over 4 and I wanted to add 2 pi to it, how much am I going to add? 8/4. So you take the denominator and you double it, and you add it to the top. So 3 and 8 is 11. It's that easy. What about a negative angle? What is 3 minus 8? Negative 5 pi over 8. Yeah, that's it. Because you're just adding a full circle. A full circle is double the denominator. So if I had something crazy like 51/60 pi, what is a coterminal positive angle? Well, you're going to add 120 to 51, 171 pi over 60, and you don't even need a calculator to do it. Okay? So that's how you're going to do the next page. Yeah, it's exactly like that problem. Double the denominator and add it to the top. So here's the tough part. What if I asked you, where does 7 pi over 6 land? Where on the, in which quadrant does 7 pi over 6 land? 1, 2, 3. Anybody want to guess 4? 4? Thanks, Connor. Well, let's think about it. This is 2 pi. This is 1 pi. So we have to think in terms of pi. When you deal in degrees, you think of in terms of the circle. Okay? So 7 pi over 6, what is this in sixths? 6 over 6. What is this in sixths? Well, 0 on top, or 12 over 6. So 7 over 6 is going to be bigger than 1. Is it closer to 1 or closer to 2? Closer to 1 would be right there. Okay? Now, let's back up a little bit, because there's another way to do this. If we're dealing in degrees, and I have 152 degrees, where is that going to land? Quadrant 2. Okay, that's easy. Let's do the division. 152 divided by 360. What does that number tell me? This is 42% of the circle. Okay, and a lot of you preferred the decimal version because it was really easy to understand. In this version, we have 0, 25, 50, 75, and 100%. Is everybody okay with that? You good? Caitlin, you? Okay. So, with radians, it works a little bit differently. Okay? In radians, you do not compare it to the entire circle. You compare it to pi, which is half the circle. So if I go back to this page and I type in 7/6, I now have 116%. Why does 116% land in 3 instead of 1? It's in comparison to pi. So this is 116% of pi. So this is 100%. What is the positive y-axis? 50%. This is 50%, and the bottom y-axis? 150, and then this is 200. Now, most students prefer the decimal version, but you need to remember, in degrees, you're talking about 100% of a circle, so it's 25, 50, 75, 100. In radians, you're talking about a portion of the top half or bottom half of the circle. So it's 50, 100, 150, and 200. Okay? So if I looked at 7 pi over 3, let's think of it in terms of fractions. How many thirds does it take to get to there? 3. Now I'm up to 6. How many more do I need? 1 more, so it's going to be quadrant 1. If I do 7 divided by 3, I get 233% of pi. Why does that land in quadrant 1? Well, 200% gets me to the beginning, and 33% is between 0 and 50, so it's in quadrant 1. Okay. What about 3 pi over 4? Where is that going to land? Are you guys lost, or? Oh, okay. Are you talking about math? Could you please? Thanks. So 3 pi over 4. Why quadrant 2? Okay, so we could do 3 over 4. 75% of the top half would be quadrant 2. What about as a fraction? So as a fraction, we're looking at either 0 or 4 over 4. Is 3/4 closer to 4 or closer to 0? Closer to 4, so it would be in quadrant 2. Roman numerals, yes. Okay, what about 2 pi over 11? So the top half is how many? 11 over 11. So is 2 closer to 11 or closer to 0? 0. What is that vertical axis? 5.5 over 11, which is kind of confusing. So 2 over 11 would be there. Let's turn it into a percent. 2/11, right, 5.5 over 11. So 18% lands in quadrant 1. Okay. What about 56/37? Pi. I have to put the pi. If you forget the pi, then it changes everything. So 56 divided by 37 is 151%. Which quadrant is that? So this is 50, 100, 150, 151. Right there. 1 pi over. Yeah, so if we had pi over 9, it's 1 over 9 pi. Yeah, so if there's not a 1 there, for calculation purposes, you have to put it there. Yeah. If you leave it blank, your calculator will freak out. And you don't want to put the pi in because then you get an irrational number. Okay, here's a tough one. 17 pi over 4. 17 divided by 4. Why 1? Good. So 1, 2, 3, 4 pi, and 25%. So that's actually the same as 45 degrees. Okay. What about 21 pi over 4? Now wait a minute. Don't they have the same decimal value? They're both 0.25, right? So why does this one land in 3 and the other one landed in 1? Well, if I looked at 850 degrees, 850 divided by 360, I can throw the 2 out and just look at 36%, correct? But in radians, is there a difference between 4.25 and 5.25? There's a big difference. In fact, a 180-degree difference, because every circle has 2. So what can you say about even numbers? They're in the top half. Right. What can you say about odd numbers? They're in the bottom. So this 5.25 means 25% of the bottom half, which would be quadrant 3. So if I had some really big number, and I divided that by, oh, I don't know, let's make something that's not going to work, 7. Where is that going to land? Okay, top or bottom half? Top half, because it's an even number. It ends in a 4. How much of the top half am I looking at? 60% of the top half, which would be quadrant 2. Nathan, you all right with that? Let's look at another one. 19/3. So 6.3. If this number is even, that guarantees I land in the top half. Because if you notice, the top half is from 0 to 1. The bottom half is from 1 to 2. And then from 2 to 3, 3 to 4, the top half is always an even number. The bottom half is always an odd number. So 6 is even, so it's in the top half. 30% of the top half would be quadrant 1. 1/3 of the top. Well, almost a third. So if I did 22/3, I now have 7.3. What does that 7 tell me? It's on the bottom. How much of the bottom? 33%. So from here to here is 100%. 33 would be there. Okay, what if I did 23/3? 66% of the bottom. So 66% of that is going to put me in quadrant 4. Okay? So your homework should be pretty simple. You can probably get most of it done in the last few minutes. I don't have answers to this. I'm sorry. I will by the time you come back tomorrow. So we'll talk about any questions you have tomorrow. Good luck.